one in particular at the moment. So it's number 4, but it asks something. It's a weird equation.
So where is it? So this was hypothetical and right side.
Yes. And I went forward, but I wasn't satisfied with how I wrote the solution. It didn't look very explicit. So I was wondering if there's a fast way to solve it. In order to get a good expression.
straightforward solution would be to use the gain function. So what is actually written here? We have this boundary condition. So was there also a boundary condition at x equals to 0? U of g
Okay. And it says that we can like write the solution for t greater than 4. It says that like it suffices to write the solution for t bigger than 4.
Yes.
I think it's easier, but
yes. So let's start solving this. So first we have these boundary conditions, so we can continue everything anti-symmetrically to the whole line. So this force on the right hand side will look like this. The simplest way to solve it is to use the gain function.
Oh, sorry, but why is it bounded from above? From like the right hand side doesn't depend on time, so it should be off to.
But this is the right hand side, which is in this function. This is heaviside theta of 1 minus x, which is 1 from 0 to 1 and then vanishes.
Yeah, but vertically. Vertically, why does stop at 1?
But this is the way of heaviside theta. It is just 1.
Yeah, but it stops at x equals 1.
Yes.
Not at t equals 1. Well, is it f? Okay, no. Oh, sorry. Yeah.
Then you will get the same code for t. Now, so this was only number 4. So if now we want to find u, we can use this formal gain function. So u of t x equals the integral from 0 to t dt prime from x minus t minus prime to x plus t minus prime d d x prime f of x prime. Well, in principle, 2 prime x prime, but in this case it is just of f of x prime. So ternary looks like this. We have t prime, we have t prime x prime plane, and we have this prime, t prime. We have so to compute u of t and x, we need to integrate this function over the following triangle. Place it over here. Let's place it about this. Degrees. So we need to integrate it over this triangle. Multiply it in half. So this is the mode of integration. Now we should ask what function we are integrating precisely. So there is this domain when f equals to 1, and that 1. And here the domain when f equals to minus 1.
So it's normal that the solution is by cases. It's normal that the solution will be split into cases. So
Of course, as the right inside was defined, it was piecewise constant. So, and of course, you can pack all these answers into some combinations of theta and other functions of this kind. Well, basically, theta should be sufficient for this kind of thing. But so sometimes maybe it's easier to integrate side theta, sometimes maybe it's easier to draw a word to understand how this works. So let us study this for some large time. I've chosen to be large to avoid studying this intermediate period for small times and have a lesser number of different victims. So, what are typical situations? Let me go them one by one. So, one situation is this. And this corresponds to t greater than to x greater than f equals 1. So here we just have this 0. Then in case then x is from t plus 1 and t. this approach to this problem, but it can also be solved in some other way, and we will see from this solution. So, in this case, this triangle is placed like this. So, here we write that u is 0. Here, u equals to 1/2 times the area of this triangle. So, something like square,
Over
over 2 or over 4. Actually. Yeah, but it is multiplied by 1/2.
Oh yeah.
So probably should be 1 quarter. So we will check this later. We will the current. So no, it vanishes when x equals to t plus 1. So it should be x minus, so t plus 1 minus x squared. Right?
Yes.
Then when x is from 1 to t. So here we will have a contribution from this domain, contribution from this domain, and stops when x equals to t minus 1. Yes,
Actually, I think that the second case also has a sub-case because when x is less than 1, you get inside the region.
No,
In the case.
t plus 1. And so here we should have one more case for this region, right?
No, I'm saying that the formula for the second case applies only when x is greater than 1.
But t is large. So
So
this was the reason
this is 1.
large t. If it is greater than 4 or gamma greater than 1. So here it should be from -1 to t. So this corresponds to the configuration of this. So this part grows linearly. And this part decays contractically in the same way. So here we can write something like this.
The small triangle has side x minus t.
So this small triangle is minus. This small triangle is of size.
Yeah, x minus t. Because when x is equal to t, it vanishes.
Yes.
So it's 1/4.
Then plus this function will be linear, has some initial value for x equals to t, and it equals to this one quarter. 1/4 plus this is the value.
Yeah, plus the height. So it's still x minus t, t minus x. Yeah, t minus x.
So it is linear function.
Yeah. The maximum is like 3 something, 3/4. So when x is minus 1, you get of course the plus a half, which is equal to okay.
Now, when we go to this region from x equals to t minus 1 to x equals 1, we just have a constant function, because the area of this part increases with the same rate of this part.
You mean in the case where x is less than t minus 1?
Yes. So there is, if t is large, there is this whole interval between 1 and t minus 1, when
Yeah.
this no, it should be correct. This line moves with constant speed, and the difference of these two areas stays constant. So.
I think it's equal to 1.
Let us, yeah, it looks like the correct answer, maybe 1.5. After we finish with this, I will show the argument to derive the same result. we enter the domain from 0 to 1 in the final part. So let us first ask about this function, whether it is time-dependent or not. So suppose that we move all this picture above. If we move this triangle above, then we see that the height of these both parts increases by the same values. So it is time-dependent. There's a line equals to U of x. And this function U of x it can be found. It is a quadratic function because when we move this point here, the area of this part does not change, but the area of this part changes quadratically. So we start from the value of 1/2, and then it is
I think it changes. Even the one right changes. There's a maximum of 1/2.
So it is 0. 0.
I think we can just suppose for simplicity that x is equal to t. Since we're moving upwards, it doesn't do anything. We can just.
No, x is from 0 to 1.
Yeah, but
And
you also are supposing that t equals x.
No, t should be large, not x.
Yeah, but we're calculating areas and it doesn't change not anything.
Well.
Just cut the bottom part. So
Yes. It's
so the left side is always a quarter.
in principle, we can also do it like this, I think. Right? Measure them with the opposite sides. Or maybe better, no, maybe better to do so you were suggesting some picture of this kind.
No, I was doing like when the left diagonal line crosses the blue line, we calculate areas only above. The left oblique line crosses the blue line.
This one. At which point?
On the left. Yeah, then you draw a horizontal line there. You just calculate the area above. Since the one on the bottom will just cancel out.
Yeah.
And the left one is constant and it's half.
So we can start on this triangle from here, right? And
On the right we can remove a square. And the top one is some quadratic.
so we can do it this. Yes, and the arrow is here, right?
Yeah.
And
But you can remove another triangle. Maybe that version. Not balancing out, but just to split the shaded region on the right, to split it into sections that are easier to calculate.
which that we propose?
Horizontal line. Yeah, exactly.
But that's still kind of good.
Yeah, it's not easy, but it's easy.
Maybe it is.
It's going to be a quadratic, like constant plus x minus half squared, because the maximum is the maximum is that 1/2. So
And it finishes at 0.
no.
Because when we approach 0, then no, actually, maybe it is easier to compute it like this. To add on the
Maybe just add triangles. But if we want to do it explicitly, we can split the figure in the bottom triangle, a left triangle, right triangle, and a rectangle, and that's and I have calculations.
but in principle, we know that it is a quadratic function because it finishes here quadratically because the size of this figure vanishes quadratically, and we know its value at x equals 1. So we know that there is no linear term because when we approach 0, we have this linearly decaying square. So we can write u is x squared over 2.
No linear term.
Yes. because then it's not right.
It's not right for you.
Because when x approaches 0, what is the, so when x goes to 0, how does it look like?
No, but for x equals 1/2, you should get
X equals 1. Okay, so what should we get for x equals 1?
3/4.
How do you see this? It will be a figure like square with a part angle. How do you know that is 3/4?
For x equals 1/2, it's like 3 equal triangles together, so it's 3/4 or 3/8, something like that. I think we need a linear term. I think we need a linear term.
Let me see this equal angles and have a picture like this. So we have this angles
Normally 6, but still 3 times something. That's some way.
Flow lessons and computations of areas so let's maybe postpone it and I will actually write solutions, answers to these problems. But let me show another simple solution of such kind of problems.
Sorry, I have a question, but in this exercise we are considering the following wave equation. So if okay, and you in the 5 case in the 5 problem is like the boundary value u of x 0 is equal to x squared.
Oh, when x equals to 0, it vanishes because we need some negative values with these positive values.
Okay, but u equal x squared over 2 is like it's like u calculated in x comma 0.
Oh, it's for x in this region. Yes. Yeah, x is from 1 to -1. you see, it's a phenomenon that there is some stationary solution that lives at 0, and there is some traveling wave which goes pretty far away. And let us try to describe this phenomenon. So you see this equation. Well, maybe actually there should be another quadratic function. Well, there's also a question about the sign of that function, probably. Let us think about this in between. So we have this equation with right hand side. And this is completed with inverse with the inverse function. So let us try to find some stationary solution of it. In this case, utility equals to 0. And we have simply u of x equals to minus equals theta of 1 minus x. So let's integrate this equation. And actually on the whole line we can multiply by sigma of x. And u of 0 is 0. We can integrate this and yet we can actually integrate this twice. This will equal to so when x is from minus 1 and 1. This equals to minus x squared over 2. Times yeah. That's all. So it looks like this. And then we continue this function. So it should have a smooth first derivative. So it will become linear after minus 1 and 1. no dysfunction firefights. And so, in principle, this well, actually, I missed all the signs here. So let us say that it equals to minus firefights. Now this now we have this function which is good in principle, but it does not satisfy the initial conditions. It solves our equation on the right hand side, but we need to fix the initial conditions. And how can we do this to be sure that both u and ut are 0? Let's solve that homogeneous equation.
It means some function that respects, some function that has the opposing initial conditions as phi, but has utt minus uxx equals 0.
Yes. And we can construct it for phi. And then we can write that it is 1/2 of phi of x plus t plus phi of x minus t minus phi of x. So this parts represent those turbulent waves. You see that if x is big enough or small enough, it has a shape of turbulent wave. And if you go to the domain close to 0, then we have some x only dependent function. And concerning the dependence of this terms, maybe indeed there will be some linear parts. let's keep this things for the homework. I also do this to check what was wrong with that computation. So, do you have any questions about these computations? Okay, so let's maybe go to the lecture.